Hi, I'm David Greenwood from Newcastle University, and I'm here to talk about my poster, which is about a piece of work we did called Frequency Response Services Designed for Energy Storage. This was a piece of work we did toward the start of the CESI project, and it was looking at how energy storage can meet the requirements of the power system to correct a large frequency event which typically occurs after either a large power station or a large amount of load is disconnected, and this leads to an imbalance between supply and demand, and that is kind of addressed by the system frequency starting to either increase or decrease. And we can correct that by injecting or either power or extra demand into the system very quickly, and energy storage is well positioned to do that because it's able to respond very quickly because it has no moving parts, it's all electronic. However, energy storage hadn't been used for that before, and so we had to investigate how different control curves could be used to enable energy storage to participate, and how much impact energy storage would have if it was able to address these types of events. So we developed a unique experimental setup in order to do this, and it comprised a combination of hardware and software using a technology called power hardware in the loop. So we were able to reproduce an electricity transmission system in an Opal RT computer, and that allowed us to conduct experiments in the lab as if we'd disconnected a real power station from the national grid, something that we obviously wouldn't be allowed to do in real life because that would be quite a high risk experiment to carry out. So we are able to disconnect a power station in this real-time simulation model. That then leads to a frequency transient as the frequency changes in response to the imbalance in load demand in supply and demand. That is corrected or measured first. The change in frequency is measured by an energy storage device in the lab, and then it provides a change in power output to help correct the frequency, and that's then read back into the model and causes it to the frequency to change as it would do in real life if that energy storage system was connected. We made a number of different findings with this experiment. One is we quantified how quickly the energy storage could respond, and it was around in 80 milliseconds, which is much faster than a conventional power station, and much faster than even the expected requirement for the service, which was within 1 second. We found that energy storage could significantly reduce the nadir of frequency, which is the biggest deviation, and we found that the energy storage could effectively manage its state of charge by having an envelope in its required response rather than a fixed line that it has to follow, as is the case with conventional response type technologies. Thank you very much.